Imagine yourself standing in the middle of an open field on a clear, moonless night. The grass is cool beneath your feet, a gentle breeze brushes against your skin, and above you, stretching from horizon to horizon, is the most ancient and magnificent sight any human being can ever witness. The night sky. Thousands of tiny points of light are scattered across that dark canvas. Some bright, some faint, some flickering, some steady. You have seen this sky before. You have glanced up at it countless times, maybe on your way home, maybe from a car window, maybe from your backyard. But tonight, something is different. Tonight, you are not just looking at the sky. Tonight, you are actually going to try to understand it. And I need to warn you right now, at the very beginning of this journey, that what you are about to discover will fundamentally alter the way you perceive your existence. Because the universe is not what you think it is. It is not the size you think it is. It is not the age you think it is, and your place within it is so spectacularly, breathtakingly, almost absurdly small that the human brain literally cannot process it. But we are going to try. Together, right now we are going to attempt something extraordinary. We are going to start from the ground beneath your feet, from this very planet, from this thin crust of rock and water and air that we call home. And we are going to travel outward. We are going to zoom out, step by step, layer by layer, scale by scale, until we reach the very edge of everything that exists, everything that can be observed, everything that light has had time to reveal to us since the beginning of time itself. And along the way, I promise you, there will be moments where your jaw will drop, moments where your mind will struggle, moments where you will feel a strange mixture of terror and wonder and humility that is unlike anything else in human experience. This is not just a science video. This is a journey into the deepest question any conscious being can ask. How big is reality? And what does that mean for us? Before we launch into the cosmos, let me share something with you that will set the stage for everything that follows. If you took the entire history of the universe, all 13.8 billion years of it, and compressed it into a single calendar year, so that the Big Bang happened on January 1st at midnight, then our entire solar system would not form until September. The dinosaurs would not appear until Christmas Day. And all of recorded human history, every empire, every war, every invention, every love story, every tragedy, every triumph, everything from the ancient Sumerians to this very moment you are watching this video, all of it would fit into the last fraction of a second before midnight on December 31st. That is how brief our existence is on the cosmic timescale. And yet, here we are, conscious beings made of atoms that were forged in the hearts of dying stars, using technology built from the elements of ancient supernovae, trying to comprehend the very universe that created us. If that does not send a shiver down your spine, I do not know what will. So let us begin. Let us take this journey. And if you are the kind of person who is genuinely curious about the universe, who wants to understand not just the facts but the meaning behind them, then do me a favor, hit that like button, subscribe to this channel, and leave a comment telling me how far you think the edge of the observable universe is from where you are sitting right now. I will reveal the answer later, and I guarantee most of you will be wrong by a factor you cannot even imagine. Now, let us start from home. You are on Earth. You know this. You have always known this. But do you really know what Earth is? I mean, truly? Let us begin with the basics, because even the basics are more extraordinary than most people realize. The planet you are standing on right now is a roughly spherical body of rock and metal with a diameter of about 12,742 kilometers. That is the distance from one side of the Earth, straight through the center, to the other side. 12,742 kilometers. That sounds like a big number, and in human terms, it is. If you got in a car and drove at 100 kilometers per hour, non-stop, no brakes, no sleep, no fuel stops, it would take you more than 5 days to drive from one side of the Earth to the other, assuming you could somehow drive straight through the planet. The circumference of the Earth, the distance around the equator, is about 40,075 kilometers. That is a journey that would take you about 16.5 days of non-stop driving. So Earth feels big. It feels vast. When you stand on a mountain and look out at the horizon, the world seems to stretch on forever. When you fly across an ocean for 10 or 12 hours, staring out the window at nothing but water, the Earth seems almost impossibly large. And for most of human history it was. The Earth was the entire world. It was everything. People lived and died within a few kilometers of where they were born, and the idea that the Earth was a sphere floating in space would have seemed like madness. But here is where our journey begins to get interesting. Because Earth, this planet that feels so enormous to us, is about to become very, very small. Let me paint a picture for you. The Earth has a layered structure, like an onion. On the very outside, you have the crust, the thin shell of solid rock that you are standing on right now. The crust is remarkably thin. Under the continents, it is about 30 to 50 kilometers thick. Under the oceans, it is even thinner, only about 5 to 10 kilometers. Now think about that for a moment. The Earth is nearly 13,000 kilometers in diameter, and the solid ground beneath your feet, the foundation of everything you have ever built, every city, every road, every building, is only a few dozen kilometers thick at most. If the Earth were the size of an apple, the crust would be thinner than the apple's skin. That is how fragile our surface is. Beneath the crust lies the mantle, a vast layer of semi-molten rock that extends down about 2,900 kilometers. The mantle is not liquid, not exactly, but it is hot enough and under enough pressure that it flows, slowly, over millions of years, like extremely thick honey. This flowing mantle is what drives plate tectonics, the movement of the continents, the creation of mountains and ocean trenches, the earthquakes and volcanic eruptions that reshape our world. Beneath the mantle lies the outer core, a layer of liquid iron and nickel about 2,200 kilometers thick, swirling and churning at temperatures comparable to the surface of the sun. This liquid metal ocean, churning deep beneath your feet right now, is what generates Earth's magnetic field, the invisible shield that protects us from the sun's deadly radiation and the constant bombardment of charged particles from space. Without this magnetic field, our atmosphere would have been stripped away by the solar wind long ago, just as it was on Mars. And at the very center of the Earth, there is the inner core, a solid ball of iron and nickel about 1,200 kilometers in radius, compressed to incredible density by the weight of everything above it, with temperatures reaching over 5,000 degrees Celsius. You are sitting on a thin shell of rock, wrapped around a churning ocean of liquid metal, surrounding a ball of solid iron hotter than the surface of the sun. And this is just the starting point of our journey. Now let us talk about the atmosphere, because the atmosphere is one of those things that we take completely for granted until we realize how impossibly thin and fragile it actually is. The Earth's atmosphere, the layer of gases that allows you to breathe, that keeps the planet warm, that protects you from the vacuum of space and the lethal radiation of the cosmos, extends upward from the surface in several layers. The troposphere, where all weather happens and where you live, extends up to about 12 kilometers. The stratosphere, home of the ozone layer, goes up to about 50 kilometers. The mesosphere extends to about 80 kilometers, and the thermosphere and exosphere stretch out to several hundred kilometers, gradually thinning into the near vacuum of space. The internationally recognized boundary of space, called the Kármán line, is at 100 kilometers above sea level. 100 kilometers. That is it. That is the distance between you and the cold, airless void. If you could drive a car straight up, you would be in space in about an hour. The entire breathable atmosphere, the layer of air dense enough to support life, is even thinner, only about 8 to 15 kilometers. And here is what really puts this in perspective. If you had a globe a standard classroom globe, the kind that sits on a desk, the atmosphere at the correct scale would be thinner than a coat of varnish painted on its surface. That shimmering blue haze you see in photographs of Earth from space, that impossibly thin blue line curving along the planet's edge, that is literally everything standing between you and instant death. Every breath you have ever taken, every cloud you have ever seen, every storm, every sunset, every rainbow, all of it exists within a layer so thin that from a cosmic perspective, it might as well not exist at all. And here is a fact that I want you to sit with for a moment, because it connects to everything we are going to explore today. When astronauts look back at Earth from space, many of them describe experiencing something called the overview effect. It is a cognitive shift, a profound emotional and psychological transformation that occurs when you see the Earth as a whole for the first time. You see this tiny, fragile, luminous sphere floating in an infinite black void, with no borders, no boundaries, no divisions visible from space, just this delicate blue marble wrapped in that impossibly thin atmosphere, and something fundamental changes inside you. Many astronauts have described it as the most powerful experience of their lives. They suddenly understand, not intellectually, but viscerally, that everything they have ever known, every person they have ever loved, every conflict they have ever witnessed, every achievement of the entire human species, all of it is contained on this one small world, and the universe around it is vast, and dark, and silent, and indifferent. Edgar Mitchell, who walked on the moon during Apollo 14, described it this way. He said that he suddenly understood that the molecules in his body, and the molecules in the spacecraft, and the molecules in his fellow astronauts had all been manufactured in an ancient generation of stars. He called it an interconnected euphoria. And this understanding, this feeling, is exactly what we are going to build toward throughout this entire journey. Because the scale of the universe is not just a collection of big numbers. It is a mirror. It reflects back to us the truth of what we are and where we are, and how improbable and precious our existence really is. So let us take our first step away from Earth. Let us travel to the moon. The moon, our closest celestial neighbour, our constant companion in the sky, the object that has inspired poets and scientists and dreamers for as long as humans have looked upward. The moon orbits the Earth at an average distance of about 384,400 kilometres. That number probably does not mean much to you in the abstract, so let me translate it. If you could drive a car to the moon at highway speed, say 100 kilometers per hour, it would take you about 160 days. That is more than 5 months of continuous driving. If you could fly there in a commercial aeroplane at about 900 kilometers per hour, it would take about 18 days. The Apollo astronauts, traveling at roughly 39,000 kilometers per hour, made the journey in about 3 days. And light, the fastest thing in the universe, covers the distance in about 1.28 seconds. That is the time it takes for light to travel from the Earth to the moon. A little over 1 second. Remember that number, because as we travel farther out, the light travel times are going to become increasingly staggering. Now here is something that most people do not realize about the Earth-Moon distance, and it is one of my favourite facts in all of astronomy. The average distance between the Earth and the Moon is about 30 Earth diameters. That sounds close, and in many diagrams and illustrations, the Moon is shown quite close to the Earth, which gives people a very misleading impression of the scale. But here is the mind-blowing part. That gap between the Earth and the Moon, those 384,000 kilometers, is large enough to fit every other planet in the solar system in a line between them. Mercury, Venus, Mars, Jupiter, Saturn, Uranus and Neptune, all lined up in a row, would fit between the Earth and the Moon with room to spare. Let that sink in. Every planet in our solar system, including gas giants large enough to swallow the Earth many times over, can fit in the space between us and our nearest neighbour. That is how big the space between objects is, even at this tiny local scale. The Moon itself is a fascinating world. It has a diameter of about 3,474 kilometers, roughly 1/4 the diameter of Earth, and a mass about 1/81st that of Earth. Its surface is covered in craters, the scars of billions of years of bombardment by asteroids and meteorites, because the Moon has no atmosphere to burn up incoming objects, and no geological activity to erase the damage. The footprints left by the Apollo astronauts in the lunar dust are still there, perfectly preserved, and they will remain there for millions of years, because there is no wind, no rain, no erosion. The Moon is a time capsule, a frozen record of the violent history of our solar system. And the Moon is not just a passive companion, it plays a crucial role in making Earth habitable. The Moon's gravitational pull is responsible for the tides in our oceans, which may have played a critical role in the origin of life by creating tidal pools where complex chemistry could occur. The Moon also stabilizes Earth's axial tilt at about 23.5 degrees, which is what gives us our seasons. Without the Moon, Earth's axis would wobble chaotically over millions of years, causing extreme climate swings that might make complex life impossible. And here is a curiosity that adds a layer of wistfulness to all of this. The Moon is slowly moving away from the Earth. Every year, the Moon drifts about 3.8 centimeters farther from us, due to tidal interactions transferring energy from Earth's rotation to the Moon's orbit. This means that billions of years ago, the Moon was much closer to the Earth, looming enormous in the sky, and the Earth's day was much shorter, only about 6 hours long. And billions of years in the future, the Moon will be so far away that total solar eclipses will no longer be possible. We happen to live in the one window of time in Earth's history when the Moon appears almost exactly the same size as the Sun in our sky, which is what makes total solar eclipses such a perfect, spectacular phenomenon that is a coincidence so extraordinary that it still gives scientists pause. Now, let us zoom out further. Let us leave the Earth-Moon system behind and consider the wider neighborhood we live in, the solar system. And to understand the solar system, we need to start with the object that dominates it, the object that contains 99.86% of all the mass in the entire solar system, the object without which none of us would exist. The Sun. The Sun is a star. It is a giant ball of hydrogen and helium, 432,000 kilometers in radius, 109 times the diameter of the Earth. If the Earth were the size of a peppercorn, the Sun would be the size of a bowling ball. The Sun's volume is so large that about 1.3 million Earths could fit inside it. Its surface temperature is about 5,500 degrees Celsius, but its core temperature is about 15 million degrees Celsius. Hot enough and dense enough that hydrogen atoms are fused together into helium, releasing enormous amounts of energy in the process. This nuclear fusion is what powers the Sun. Every single second, the Sun converts about 600 million tons of hydrogen into helium, and in the process about 4 million tons of matter are converted into pure energy according to Einstein's famous equation, E equals mc squared. 4 million tons of matter annihilated and turned into light and heat every single second. And the Sun has been doing this for 4.5 billion years, and it has enough hydrogen fuel to continue doing it for another 5 billion years. The energy produced in the Sun's core takes about 100,000 years to fight its way outward through the dense layers of the Sun to the surface, and then it radiates outward into space as sunlight. The light that is warming your face right now was generated in the core of the Sun 100,000 years ago. It began its outward journey when Neanderthals still walked the Earth, and once that light left the Sun's surface, it took only about 8 minutes and 20 seconds to cross the 150 million kilometers of empty space between the Sun and the Earth. That distance, 150 million kilometers, is so important in astronomy that it has its own name. 1 astronomical unit, or 1 AU. This is going to be our measuring stick for the inner solar system. The Sun is not just big, it is violent. Its surface is a roiling, churning, explosive maelstrom of superheated plasma. Enormous loops of magnetic field lines burst from the surface, creating structures called solar prominences that can extend hundreds of thousands of kilometers into space. Arches of fire larger than the entire planet Earth. Sunspots, dark patches on the Sun's surface caused by intense magnetic activity, can be larger than Earth. And occasionally, the Sun releases massive bursts of charged particles called coronal mass ejections, which can send billions of tons of magnetized plasma hurtling through space at millions of kilometers per hour. When these hit Earth's magnetic field, they cause geomagnetic storms that create the beautiful auroras, the northern and southern lights. But they can also disrupt satellites, communications and power grids. In 1859, a massive solar storm called the Carrington Event hit Earth and was so powerful that telegraph systems caught fire and auroras were visible as far south as the Caribbean. If a storm of that magnitude hit Earth today, with our dependence on electronics and satellites, the damage could be in the trillions of dollars and could take months or even years to repair. The Sun, our life giver, is also a constant reminder that we live at the mercy of cosmic forces far beyond our control. Let us now take a tour of the inner solar system, starting with the planet closest to the Sun, Mercury. Mercury is the smallest planet in our solar system, with a diameter of about 4,879 kilometers, only slightly larger than our Moon. It orbits the Sun at an average distance of about 58 million kilometers, or 0.39 AU. Because it is so close to the Sun, Mercury has an extremely eccentric orbit and a very slow rotation, which creates some of the most extreme temperature swings in the solar system. On the side facing the Sun, temperatures can reach 430 degrees Celsius, hot enough to melt lead. On the night side, temperatures plummet to minus 180 degrees Celsius. Mercury has virtually no atmosphere, just a thin exosphere of atoms blasted off its surface by the solar wind. It is a cratered, barren, baked world, and yet it holds secrets. Mercury has a disproportionately large iron core, making up about 85% of the planet's radius, which suggests that it may have once been a much larger planet that had its outer layers stripped away by a massive collision early in its history. And despite being so close to the Sun, Mercury actually has ice in permanently shadowed craters near its poles, where sunlight has never reached, water ice, sitting on the closest planet to the Sun. The universe is full of surprises. Next comes Venus, and Venus deserves special attention because it is often called Earth's twin, a name that is both accurate and deeply misleading. Venus is almost the same size as Earth, with a diameter of about 12,104 kilometers. It has a similar mass, a similar density, a similar composition. If you were designing a solar system and you wanted to make a spare Earth, Venus would be your starting template. And yet Venus is the most hellish planet in the inner solar system. Its atmosphere is 96% carbon dioxide, and it is incredibly thick. The atmospheric pressure at the surface of Venus is about 92 times the pressure at Earth's surface. That is equivalent to being almost a kilometer deep in Earth's ocean. This thick carbon dioxide atmosphere has created a runaway greenhouse effect so extreme that the surface temperature of Venus is about 465 degrees Celsius, even hotter than Mercury. Even though Venus is nearly twice as far from the Sun, it is hot enough to melt lead, hot enough to glow dull red in the dark. The clouds of Venus are made of sulfuric acid, and the planet is shrouded in a permanent opaque cloud layer that prevents you from ever seeing the surface from space. Soviet Venera probes that landed on Venus in the 1970s and 80s survived for only minutes to about 2 hours before being crushed and melted by the extreme conditions. The images they sent back show a barren, rocky landscape under a thick orange-yellow sky with visibility of only a few kilometers. Venus rotates backwards compared to most other planets, and its rotation is so slow that a single Venusian day is longer than a Venusian year. It takes the planet 243 Earth days to complete one rotation, but only 225 Earth days to orbit the Sun. Venus is a powerful and terrifying example of what happens when a greenhouse effect runs away, and some scientists consider it a warning of what could happen to Earth if we are not careful with our own atmosphere. Now we come back to Earth, the third planet from the Sun, and we have already discussed our home in some detail, so let us move on to the fourth planet, the one that has captured human imagination more than any other: Mars. Mars, the red planet, named after the Roman god of war because of its blood-red appearance in the night sky, is a world that has fascinated humanity for centuries. It has a diameter of about 6,779 kilometers, roughly half the size of Earth, and a mass only about 1/10 of Earth's. Mars orbits the Sun at an average distance of about 228 million kilometers, or 1.52 AU. Its thin atmosphere, only about 1% the density of Earth's, is mostly carbon dioxide, and it provides almost no insulation, so surface temperatures average about -60 degrees Celsius, though they can range from -140 at the poles in winter to a relatively balmy 20 degrees Celsius at the equator in summer. But what makes Mars truly spectacular is its geology. Mars is home to Olympus Mons, the tallest volcano in the entire solar system. Olympus Mons stands about 21.9 kilometers above the surrounding terrain, nearly 2.5 times the height of Mount Everest above sea level. Its base is so wide, about 600 kilometers in diameter, that if you were standing on its slopes, you would not be able to see the summit, because it would be beyond the curvature of the horizon. Mars is also home to Valles Marineris, a canyon system so vast that it would stretch from New York to Los Angeles if placed on Earth. It is up to 7 kilometers deep and 200 kilometers wide in places. The Grand Canyon, by comparison, could fit as a minor side branch. And here is the question that makes Mars more than just a geological curiosity. Mars has dry riverbeds, mineral deposits that can only form in the presence of liquid water, and polar ice caps made of water ice and carbon dioxide ice. The evidence is overwhelming that Mars once had liquid water on its surface, possibly even oceans. There is even recent evidence of briny liquid water seeping on the surface today in certain conditions. Where there was water, there may have been life. And so the question that drives much of our Mars exploration is one of the most profound questions in all of science. Was there ever life on Mars? And if so, is it still there, perhaps clinging to existence deep underground in liquid water reservoirs? We do not yet have the answer, but we are closer than ever to finding out. Before we leave the inner solar system, let us pause to appreciate the asteroid belt, which lies between the orbits of Mars and Jupiter at a distance of roughly 2.2 to 3.2 AU from the Sun. Popular culture often depicts the asteroid belt as a dense, dangerous field of tumbling rocks, where spaceships must dodge and weave to avoid destruction. The reality is far less dramatic. The asteroid belt is vast, and the asteroids within it are very widely spaced. If you were standing on one asteroid and looked around, the nearest visible asteroid would likely be too far away to see with the naked eye. Spacecraft have passed through the asteroid belt many times without any special maneuvering and without coming close to any asteroid. The total mass of all the asteroids in the belt combined is less than 4% of the mass of our Moon. Ceres, the largest object in the belt, has a diameter of about 940 kilometers and is classified as a dwarf planet. It contains about a third of the total mass of the belt all by itself. The asteroid belt exists because Jupiter's immense gravity prevented the material in that region from ever coalescing into a planet. It is a graveyard of a world that never was. And now, we arrive at the true giant of our solar system, Jupiter. Jupiter is so large, so massive, and so important to the dynamics of our solar system that it deserves our careful attention. Jupiter has a diameter of about 139,820 kilometers, which means you could line up about 11 Earths side by side across its face. But diameter does not capture the full picture. Jupiter's volume is about 1,321 times that of Earth. You could fit more than 1,300 Earths inside Jupiter. Its mass is about 318 times that of Earth, and it is 2.5 times more massive than all the other planets in the solar system combined. Jupiter is not just a planet. It is almost a solar system unto itself. In fact, if Jupiter had been about 80 times more massive, it would have had enough mass for nuclear fusion to ignite in its core, and it would have become a star. Our solar system would have been a binary star system. Jupiter orbits the Sun at an average distance of about 778 million kilometers, or 5.2 AU. Light from the Sun takes about 43 minutes to reach Jupiter. And here is where the distances start to really hit you. Mercury, the closest planet to the Sun, is about 58 million kilometers away. Jupiter is about 778 million kilometers away. That is more than 13 times farther. The distances are growing exponentially, and we are still well within our solar system. Jupiter's atmosphere is a swirling masterpiece of chemistry and physics. Its famous bands of color are created by different chemical compounds in its upper atmosphere, ammonia ice crystals, ammonium hydrosulfide and water, being stretched into horizontal bands by Jupiter's extremely rapid rotation. Despite its enormous size, Jupiter rotates faster than any other planet, completing one rotation in just under 10 hours. This rapid rotation creates the distinctive banded appearance and generates powerful jet streams with wind speeds reaching up to 620 kilometers per hour. And then there is the Great Red Spot. The Great Red Spot is an anticyclonic storm, a massive high-pressure system that has been raging on Jupiter for at least 350 years. We know this because it was first observed through telescopes in the 17th century, and it may be much older than that. At its largest, the Great Red Spot was about 40,000 kilometers across, large enough to swallow 2 or 3 Earths side by side. It has been shrinking in recent decades, but it is still the largest storm in the solar system. Imagine a hurricane on Earth, the most powerful force of nature we experience. And then imagine one that is larger than our entire planet and has been raging for centuries. That is Jupiter, but Jupiter's moons might be even more fascinating than Jupiter itself. Jupiter has at least 95 known moons, but 4 of them are so large and so important that they were among the first objects Galileo Galilei observed through his telescope in 1610, and they changed our understanding of the universe forever. They are called the Galilean moons, Io, Europa, Ganymede, and Callisto. Io is the innermost of the 4, and it is the most volcanically active body in the entire solar system. Jupiter's immense gravitational pull, combined with the gravitational tugs of Europa and Ganymede, creates tidal forces that squeeze and stretch Io's interior, generating enormous amounts of heat. This heat drives hundreds of active volcanoes that continuously coat Io's surface in fresh sulfur and sulfur dioxide, giving it a vivid yellow, orange, and red appearance that has been compared to a pizza. Europa, the next moon out, is possibly the most intriguing world in our solar system from the perspective of finding extraterrestrial life. Europa's surface is a shell of water ice, but beneath that shell, heated by the same tidal forces that make Io volcanic, there is almost certainly a global ocean of liquid water. This ocean is estimated to contain about 2 to 3 times as much water as all the oceans on Earth combined. And where there is liquid water and energy, there is the potential for life. Hydrothermal vents on Europa's ocean floor, similar to those on Earth's ocean floor that support thriving ecosystems of chemosynthetic organisms, could provide the energy and chemistry needed for life. Ganymede is the largest moon in the solar system, larger even than the planet Mercury, with a diameter of about 5,268 kilometers. It is the only moon known to have its own magnetic field. And Callisto, the outermost Galilean moon, is one of the most heavily cratered objects in the solar system, a battered ancient surface that records billions of years of impacts. Jupiter and its moons are like a miniature solar system, and they remind us that the potential for interesting and complex worlds is not limited to planets. Jupiter also plays a crucial role in protecting the inner solar system. Its enormous gravity acts like a cosmic shield, deflecting or capturing many comets and asteroids that might otherwise make their way toward Earth. This was dramatically demonstrated in 1994, when comet Shoemaker-Levy 9, broken into fragments by Jupiter's tidal forces, slammed into Jupiter's atmosphere over a period of several days, creating explosion scars larger than the Earth. Some scientists believe that without Jupiter's protective gravitational influence, the rate of catastrophic impacts on Earth would be much higher, and complex life might never have had the chance to evolve. Jupiter is, in a sense, our guardian. Beyond Jupiter lies the second of the solar system's gas giants, and arguably the most beautiful planet of all, Saturn. Saturn, the jewel of the solar system, is instantly recognizable by its magnificent ring system. Saturn has a diameter of about 116,460 kilometers, making it the second largest planet after Jupiter. You could fit about 764 Earths inside Saturn. But here is a fact that seems almost impossible. Despite its enormous size, Saturn is less dense than water. Saturn's average density is about 0.687 grams per cubic centimeter, while water is 1 gram per cubic centimeter. This means that if you could somehow find a bathtub large enough, Saturn would float. It is a giant ball of hydrogen and helium, so puffy and low density that it would bob on the surface of a cosmic ocean like a beach ball. Saturn orbits the Sun at an average distance of about 1.43 billion kilometers, or 9.58 AU. Light from the Sun takes about 79 minutes to reach Saturn. We are now more than an hour's light travel time from home. Saturn's rings are one of the most visually stunning features in the entire solar system. They extend from about 6,600 kilometers to about 120,000 kilometers above Saturn's equator, giving the ring system a total span of about 282,000 kilometers from edge to edge. That is about 70% of the distance from the Earth to the Moon. And yet, despite their enormous width, Saturn's rings are astonishingly thin. In most places, they are only about 10 meters thick. Some regions are even thinner, just a few meters. If you scaled Saturn's rings down so that their diameter was the size of a football field, their thickness would be about 10,000 times thinner than a razor blade. The rings are made up of countless individual particles, ranging in size from tiny grains of sand to chunks of ice as large as houses, and they are composed almost entirely of water ice, with a small amount of rocky debris. How the rings formed is still debated, but the leading theories suggest they may be the remnants of a moon or comet that was torn apart by Saturn's gravitational tidal forces, or that they are leftover material from the formation of the solar system that was never able to coalesce into a moon. Recent data from the Cassini mission, which orbited Saturn from 2004 to 2017, suggests that the rings may be surprisingly young, perhaps only 100 to 200 million years old, which means they did not exist when dinosaurs roamed the Earth. Saturn's rings may be a temporary feature, slowly raining material onto Saturn and slowly being eroded, and they may eventually disappear entirely in another 100 million years or so. We are lucky to be alive to see them. Saturn, like Jupiter, has a vast family of moons, with over 140 confirmed satellites. And 2 of these moons are among the most scientifically fascinating worlds in the solar system. Titan, Saturn's largest moon, is the second largest moon in the solar system after Ganymede, with a diameter of about 5,150 kilometers. Titan is unique among moons because it has a thick, dense atmosphere, thicker than Earth's in fact, with a surface pressure about 1.5 times that of Earth. Titan's atmosphere is primarily nitrogen, like Earth's, but it contains significant amounts of methane and other hydrocarbons, which give it its orange, hazy appearance. And here is what makes Titan truly extraordinary. It has a liquid cycle, similar to Earth's water cycle, but based on methane and ethane instead of water. Titan has methane rain, methane rivers, and methane lakes and seas. The Cassini spacecraft's Huygens probe, which landed on Titan's surface in 2005, sent back images of a world with river channels carved into its surface, rounded pebbles of water ice smoothed by flowing liquid methane, and a thick, hazy sky. Titan is the only body in the solar system besides Earth that has stable liquids on its surface, and some scientists speculate that exotic forms of life, based on liquid methane rather than liquid water, could potentially exist there. It is a world that challenges our very definition of what a habitable environment looks like. And then there is Enceladus, a much smaller moon only about 500 kilometers in diameter, which has become one of the most exciting targets in the search for extraterrestrial life. In 2005, the Cassini spacecraft discovered enormous geysers of water ice erupting from fractures near Enceladus's south pole, shooting plumes of material hundreds of kilometers into space. Analysis of these plumes revealed that they contain water vapor, ice particles, salts, and complex organic molecules, strongly suggesting that beneath Enceladus's icy surface there is a subsurface ocean of liquid water in contact with a rocky core. Hydrothermal activity on the ocean floor could provide the energy and chemistry needed for life. Enceladus, this tiny, unassuming moon, may harbour a warm, salty ocean beneath its frozen surface, and that ocean might contain life. We will not know for certain until we send a dedicated mission to investigate, but the possibility is tantalizing. Let us continue our outward journey to the ice giants, the two most distant planets in our solar system, Uranus and Neptune. These worlds are fundamentally different from the gas giants Jupiter and Saturn. While Jupiter and Saturn are composed primarily of hydrogen and helium, Uranus and Neptune are made mostly of heavier elements, water, ammonia, and methane, compressed into a hot, dense fluid. This is why they are called ice giants rather than gas giants. Uranus orbits the Sun at an average distance of about 2.87 billion kilometers, or 19.2 AU. Light from the Sun takes about 2 hours and 40 minutes to reach Uranus. Neptune, the outermost planet, orbits at about 4.5 billion kilometers, or 30.1 AU. Sunlight takes about 4 hours and 10 minutes to reach Neptune. We are now so far from the Sun that it would appear as just a very bright star in the sky, still the brightest object, but no longer the blazing disk we see from Earth. Uranus is a strange planet in many ways. It has a diameter of about 50,724 kilometers, making it the third largest planet in the solar system. But its most distinctive feature is its axial tilt. While most planets rotate roughly upright relative to their orbital plane, Uranus is tilted over by about 97.8 degrees. It essentially rotates on its side, like a ball rolling along the ground, rather than spinning like a top. This extreme tilt means that during its 84-year orbit around the Sun, each pole gets about 42 years of continuous sunlight, followed by 42 years of darkness. The leading theory for this extreme tilt is that early in its history, Uranus was struck by an Earth-sized object that knocked it over. Uranus's blue-green color comes from methane in its atmosphere, which absorbs red light and reflects blue and green. Despite being farther from the Sun than Neptune in some ways receives less internal heat, Uranus is actually the coldest planet in the solar system, with cloud top temperatures dipping as low as -224 degrees Celsius. It radiates very little heat compared to its absorbed sunlight, making it something of a thermal mystery. Neptune, the eighth and final planet, is a world of extremes. It has a diameter of about 49,244 kilometers, slightly smaller than Uranus but more massive due to its higher density. Neptune's atmosphere is similar to Uranus's, with hydrogen, helium and methane giving it a striking deep blue color. But what makes Neptune truly remarkable is its weather. Neptune has the fastest winds of any planet in the solar system, with speeds reaching up to 2,100 kilometers per hour. That is faster than the speed of sound on Earth. The question of how a planet so far from the Sun, receiving so little solar energy, can generate such powerful storms is still not fully understood. but it is believed that Neptune's internal heat source, which radiates about 2.6 times more energy than it receives from the Sun, drives these extreme weather systems. When the Voyager 2 spacecraft flew by Neptune in 1989, it discovered a massive storm system called the Great Dark Spot, similar to Jupiter's Great Red Spot, but in a deep blue atmosphere. Neptune has a system of faint rings, much less spectacular than Saturn's but still present, and it has 14 known moons, the largest of which is Triton. Triton is a fascinating world in its own right. It is one of the coldest objects in the solar system, with surface temperatures around -235 degrees Celsius. It orbits Neptune in a retrograde direction, meaning it orbits opposite to Neptune's rotation, which strongly suggests that Triton is a captured Kuiper Belt object, a world that was passing by Neptune billions of years ago and was snared by Neptune's gravity. Triton has geysers that erupt nitrogen gas and dark dust particles several kilometers above its surface, making it one of the few geologically active moons in the solar system. Now we pass beyond the orbit of Neptune, and we enter a region of the solar system that was largely unknown until the 1990s, the Kuiper Belt. The Kuiper Belt is a vast, roughly donut-shaped region of space extending from about 30 AU to approximately 50 AU from the Sun, filled with hundreds of thousands of icy bodies, remnants from the formation of the solar system 4.5 billion years ago. The most famous Kuiper Belt object is of course Pluto. Pluto was discovered in 1930 and was considered the 9th planet for 76 years before being reclassified as a dwarf planet in 2006. Pluto has a diameter of about 2,377 kilometers, smaller than our Moon, and it orbits the Sun at an average distance of about 39.5 AU, though its highly eccentric orbit sometimes brings it closer to the Sun than Neptune. For most of its history since discovery, Pluto was just a tiny dot of light, a mysterious object at the very edge of the known solar system. But in July 2015, NASA's New Horizons spacecraft flew by Pluto after a 9.5-year journey, and the images it sent back changed everything. Pluto turned out to be a remarkably complex and beautiful world. Its surface features a vast, heart-shaped glacier of nitrogen ice called Tombor Regio, named after Clyde Tombaugh, who discovered Pluto. Mountains of water ice, several kilometers high, rise from the surface. The nitrogen atmosphere creates a blue haze when backlit by the Sun. Pluto has 5 known moons, the largest of which, Charon, is so large relative to Pluto that the two orbit a common center of gravity between them, making them almost a double dwarf planet system. The New Horizons flyby was one of the greatest achievements of space exploration, transforming Pluto from a smudge of light into a real, detailed, magnificent world. But the Kuiper Belt is just the beginning of the outer solar system. Beyond the Kuiper Belt, there is a region called the scattered disk, home to icy objects that have been gravitationally scattered by the outer planets into highly elliptical orbits. Eris, one of the largest known dwarf planets, resides in the scattered disk at a current distance of about 96 AU from the Sun. And beyond the scattered disk, far, far beyond it, there may lie the most vast structure associated with our solar system, the Oort cloud. The Oort cloud is a theoretical shell of icy objects that is thought to surround the solar system at distances ranging from about 2,000 AU to as far as 100,000 AU, or roughly 1.5 light-years from the Sun. We have never directly observed the Oort cloud, because its constituent objects are too far away, too small, and too faint to detect with current technology. But we know it must exist because of long-period comets. Comets that take thousands or millions of years to complete one orbit around the Sun must come from somewhere very far away, and the Oort cloud is the most logical reservoir. The Oort cloud is thought to contain trillions of icy objects, and its total mass may be several times that of Earth. If the Oort cloud extends to 100,000 AU, as some models suggest, then the Sun's gravitational influence, and therefore the solar system, extends nearly 2 light-years in every direction. Let me repeat that. Our solar system, if we include the Oort cloud, may be almost 4 light-years across. and the nearest star, Proxima Centauri, is about 4.24 light-years away. This means the outer edges of our solar system's Oort cloud may almost reach the outer edges of Proxima Centauri's equivalent cloud. The gap between star systems may be much smaller than we think, at least in terms of their gravitational spheres of influence, and yet the stars themselves, the actual balls of burning hydrogen at the centers of those systems, are still incredibly, impossibly far apart. Let us talk about Voyager 1. Voyager 1 is the farthest human-made object from Earth, launched on September 5, 1977. It has been traveling through space for nearly 5 decades. As of now, Voyager 1 is approximately 160 AU from the Sun. It is traveling at about 17 kilometers per second, or roughly 61,000 kilometers per hour. That is fast. Incredibly fast by human standards. And yet, at that speed, Voyager 1 would need about 300 years to reach the inner edge of the Oort cloud, and about 30,000 years to pass through it. And it would take about 73,000 years to reach the distance of Proxima Centauri, though it is not heading in that direction. Voyager 1 is currently in interstellar space, having crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium in August 2012. It was the first human-made object to enter interstellar space. But even though Voyager 1 has left the Sun's heliosphere, it has not left the solar system, not by a long shot. It is still deep within the Sun's gravitational influence, still arguably within the outermost reaches of our star's domain. Voyager 1 carries a golden record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. It includes greetings in 55 languages, music from different cultures and eras, sounds of nature, and encoded images. It is a message in a bottle cast into the cosmic ocean, a testament to human hope and curiosity. The chances of any extraterrestrial civilization ever finding it are astronomically small, but the fact that we sent it at all says something profound about who we are. And on February 14th, 1990, when Voyager 1 was about 6 billion kilometers from Earth, the spacecraft turned its camera around one last time and took a series of photographs of the solar system at the urging of astronomer Carl Sagan. One of those photographs captured Earth as a tiny speck of light, less than a pixel in size, suspended in a ray of scattered sunlight. That image became known as the pale blue dot, and it is perhaps the most important photograph ever taken. Carl Sagan wrote about it with words that I think every human being should hear at least once in their lives. He said, "Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. Every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." That image and those words capture something essential about the journey we are taking today, because as we zoom out further and further, Earth is going to become smaller and smaller, until it disappears entirely, lost in the vastness. And that is not a reason for despair, it is a reason for wonder. Now, let us take the next great leap. Let us leave the solar system entirely and venture into the stars. And to do that, we need to grapple with a unit of measurement that is both elegantly simple and utterly mind-breaking: the light year. A light year is the distance that light travels in 1 year. Light moves at approximately 299,792.458 kilometers per second. In 1 year, that adds up to about 9.461 trillion kilometers. 9.461 trillion. Let me try to put that in perspective. If you could drive a car at 100 kilometers per hour, it would take you about 108 million years to travel 1 light year. If you could fly in a commercial aeroplane at 900 kilometers per hour, it would take about 12 million years. Even the space shuttle, traveling at about 28,000 kilometers per hour, would take almost 40,000 years to travel 1 light-year. Light is the fastest thing in the universe. Nothing can exceed it. And yet, as we are about to see, light is hopelessly, painfully slow compared to the distances it needs to cover. The nearest star system to our Sun is Alpha Centauri, a triple star system located about 4.37 light-years away. The system consists of Alpha Centauri A, a star slightly larger and brighter than our Sun, Alpha Centauri B, a slightly smaller and dimmer star, and Proxima Centauri, a small red dwarf star that is the closest individual star to our Sun at 4.24 light-years. These 3 stars orbit each other in a complex gravitational dance, with Alpha Centauri A and B orbiting each other relatively closely, while Proxima Centauri orbits the pair at a much greater distance. In 2016, astronomers announced the discovery of an exoplanet orbiting Proxima Centauri in the star's habitable zone, the region where temperatures could allow liquid water to exist on the surface. This planet, called Proxima Centauri B, has a minimum mass of about 1.3 times that of Earth, and it orbits its star at a distance of about 7.5 million kilometers, completing one orbit every 11.2 days. Because Proxima Centauri is a red dwarf, much smaller and cooler than our Sun, the habitable zone is much closer to the star. But Proxima Centauri is also known for its powerful stellar flares, which could strip away a planet's atmosphere and bombard its surface with harmful radiation. Whether Proxima B could actually support life is one of the most tantalizing open questions in modern astronomy. 4.24 light-years. Let me help you feel that distance. Let us use a scale model. Imagine that the Sun is a grapefruit, about 10 centimeters in diameter, sitting on a table in front of you. At this scale, the Earth would be a tiny grain of sand, about 1 millimeter in diameter, sitting about 10 meters away. Jupiter would be a marble about 1 centimeter across, about 50 meters away. Neptune would be a small pea about 300 meters away. And Proxima Centauri? At this scale, with the Sun as a grapefruit on your table, Proxima Centauri would be another small object, a cherry perhaps, sitting about 270 kilometers away. That is the distance from London to Paris, or from New York to Washington, D.C. The solar system, at this scale, fits within a few hundred meters. The nearest star is hundreds of kilometers away. That is the reality of interstellar distances. The stars are unfathomably far apart. And this is just the nearest star. Let us expand our view a little further. Within about 10 light-years of the Sun, there are about a dozen known star systems. Barnard's star, a red dwarf, is about 6 light-years away. Wolf 359, another red dwarf made famous by Star Trek, is about 7.9 light-years away. Sirius, the brightest star in the night sky, is about 8.6 light-years away. Sirius is actually a binary system. Sirius A, a bright white main sequence star about twice the mass of our Sun, and Sirius B, a white dwarf, the dense remnant of a star that has exhausted its nuclear fuel. Within about 20 light-years, there are roughly 130 known star systems, and here is something that might surprise you. The vast majority of these stars are red dwarfs. Small, cool, dim stars that are invisible to the naked eye. In fact, red dwarfs make up about 70 to 75% of all stars in the Milky Way. They are the most common type of star by far, and yet you cannot see a single one without a telescope. Every star you can see in the night sky with your naked eye is more luminous than average. The night sky you see is a highly biased sample. The universe is mostly lit by stars too dim for your eyes to detect. Let us continue zooming out. As we expand our view to hundreds of light years, we begin to see the local structure of our region of the Milky Way. Our solar system is currently passing through a relatively thin cloud of warm, partially ionized gas called the local interstellar cloud, which is about 30 light years across. We have been inside this cloud for roughly the last 44,000 to 150,000 years, and we will exit it in the next 10 to 20,000 years. This cloud is in turn located within a much larger structure called the local bubble, a cavity in the interstellar medium about 300 light-years in diameter. The local bubble was carved out by a series of supernovae that occurred in our neighborhood over the past 10 to 20 million years. These massive stellar explosions cleared away much of the gas and dust in our region, creating a hot, low-density cavity. The Sun is currently located near the center of this bubble, which is one reason why we have such a clear view of distant stars. There is relatively little interstellar dust to block our view compared to other regions of the galaxy. As we look out from our position within the local bubble, we can see into neighboring bubbles and regions of denser interstellar gas, including the famous star-forming regions that are visible as nebulae. Nebulae are among the most visually spectacular objects in the universe, and they come in several types. Emission nebulae are clouds of ionized gas that glow because the atoms within them are energized by ultraviolet radiation from nearby hot stars. The Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion's sword, is one of the most famous emission nebulae. It is located about 1,340 light-years from Earth and is a stellar nursery, a region where new stars are being born right now. The Eagle Nebula, about 7,000 light-years away, contains the iconic Pillars of Creation, towering columns of gas and dust several light-years tall, within which new stars are forming. Reflection nebulae glow by reflecting the light of nearby stars, and dark nebulae are dense clouds of gas and dust that block the light of objects behind them, appearing as dark silhouettes against brighter backgrounds. The Horsehead Nebula in Orion is a famous example of a dark nebula, and planetary nebulae, despite their misleading name, have nothing to do with planets. They are the beautiful glowing shells of gas expelled by dying sun like stars in the final stages of their lives. The Ring Nebula and the Cat's Eye Nebula are stunning examples. These nebulae are the universe's way of recycling material. Stars form from clouds of gas, burn for millions or billions of years, and then return much of their material to space when they die, enriched with heavier elements that were forged in their cores. This enriched material then becomes part of the next generation of stars and planets. Every atom in your body that is heavier than hydrogen and helium was created inside a star that lived and died before our sun was born. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was synthesized in the nuclear furnaces of ancient stars, scattered into space by their deaths, and incorporated into the cloud of gas that collapsed to form our solar system 4.5 billion years ago. You are, quite literally, made of star stuff. That is not a metaphor, it is a scientific fact. Now let us zoom out dramatically and consider the full scale of our home galaxy, the Milky Way. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which spiral arms extend outward. It has a diameter of about 100,000 to 180,000 light-years, depending on how you define its edges. Because the boundaries of galaxies are not sharp, but gradually fade into the intergalactic medium. The disk of the galaxy, where most of the stars are concentrated, is about 1,000 to 2,000 light-years thick. The central bulge, a dense, roughly spherical concentration of older stars at the center of the galaxy, extends about 10,000 light-years from the center, and surrounding the disk and bulge is the galactic halo, a roughly spherical region extending perhaps up to 300,000 light-years from the center, containing old stars, globular clusters, and a vast amount of dark matter. Our Sun is located in the disk of the Milky Way, about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm, or sometimes the Orion Spur, which sits between two major arms, the Perseus Arm and the Sagittarius Arm. We are not at the center of the galaxy, not at the edge, but somewhere in between, in a relatively quiet suburb of a vast galactic city. The number of stars in the Milky Way is estimated to be between 100 billion and 400 billion. Let me try to make that number real for you. If you started counting stars at a rate of 1 per second, without sleeping, without stopping, it would take you about 3,170 years to count to 100 billion. And that is the low estimate. Some models put the number of stars closer to 400 billion, which would take you about 12,700 years to count. And each of those stars is a sun, a nuclear furnace, potentially with its own system of planets orbiting it. Current estimates suggest that there is, on average, at least one planet per star in the Milky Way. That means there are at least 100 billion to 400 billion planets in our galaxy alone. And of those, a significant fraction are expected to be rocky, Earth-sized planets in the habitable zones of their stars. The numbers are staggering. The potential for other worlds, other environments, other conditions where life could arise is immense. The Milky Way's spiral arms are not solid structures, but rather density waves, regions of slightly higher density that move through the galactic disk like traffic jams on a highway. As gas and dust move into these density waves, they are compressed, triggering the formation of new stars. This is why spiral arms appear bright. They are lit up by hot, young, luminous stars that formed recently within the compressed gas. Older, cooler stars are distributed more evenly throughout the disk. Our solar system orbits the center of the Milky Way at a speed of about 828,000 kilometers per hour, that is 230 kilometers per second. Even at that incredible speed, it takes about 225 to 250 million years to complete one orbit. This period is sometimes called a galactic year, or a cosmic year. In the 4.5 billion years since the Sun formed, it has completed about 18 to 20 orbits around the galaxy. The last time the Sun was at this point in its orbit, dinosaurs were just beginning to appear on Earth. The time before that, the first complex multicellular life was emerging. The Milky Way's rotation is a clock that ticks on timescales almost beyond comprehension. At the very center of the Milky Way lurks an object that represents one of the most extreme phenomena in the entire universe, a supermassive black hole called Sagittarius A star. We cannot see it directly because it is hidden behind dense clouds of gas and dust in the galactic center, but we know it is there because we can observe its gravitational effects on the stars orbiting near it. For over 2 decades, astronomers have tracked the orbits of stars in the immediate vicinity of Sagittarius A star, watching them whip around an invisible point at tremendous speeds. One star, called S2, orbits the black hole in just 16 years and reaches speeds of almost 3% the speed of light at its closest approach. From these observations, we can calculate the mass of the invisible object, about 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing the shadow of the black hole surrounded by a glowing ring of superheated gas. It was a historic achievement, a direct visual confirmation of the monster at the heart of our galaxy. Let us talk about black holes more broadly, because they are among the most fascinating and terrifying objects in the universe, and understanding them is crucial to understanding the cosmic scale. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape once it crosses the boundary, known as the event horizon. Black holes are formed when massive stars, those with more than about 20 to 25 solar masses, exhaust their nuclear fuel and can no longer support themselves against their own gravity. The core collapses, and if it is massive enough, it collapses all the way down to a singularity, a point of theoretically infinite density. The event horizon is not a physical surface, but a mathematical boundary, the radius at which the escape velocity equals the speed of light. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole with 1 million solar masses, the event horizon would have a radius of about 3 million kilometers. And for the most massive black holes known, with billions of solar masses, the event horizon can be larger than the orbit of Neptune, stellar black holes, formed from the deaths of massive stars, typically have masses between 5 and 20 solar masses. They are scattered throughout the galaxy, perhaps hundreds of millions of them in the Milky Way alone, but they are incredibly difficult to detect because they are small and emit no light. We can only detect them when they are in binary systems, pulling matter from a companion star, or when they merge with other compact objects, producing gravitational waves that ripple through space-time. In 2015, the LIGO Observatory made the first direct detection of gravitational waves, produced by the merger of two stellar black holes about 1.3 billion light-years away. This was one of the most important scientific discoveries of the 21st century, opening an entirely new way of observing the universe. Then there are the supermassive black holes, the true monsters. These behemoths, with masses ranging from millions to tens of billions of solar masses, reside at the centers of most, if not all, large galaxies. How they form is still one of the biggest open questions in astrophysics. They may grow from smaller black hole seeds that form in the early universe, and then grow by accreting gas and merging with other black holes over billions of years. When a supermassive black hole is actively consuming large amounts of matter, the material forms a swirling accretion disk around the black hole, heated to millions of degrees, and the system becomes an active galactic nucleus, or AG. The most extreme AGNs are quasars, which are so luminous that they can outshine their entire host galaxy, hundreds of billions of stars, by factors of hundreds or even thousands. A single quasar can emit more energy than 1 trillion suns. Quasars are powered by supermassive black holes, consuming the equivalent of several solar masses of material per year, converting a significant fraction of that mass into energy through the incredible efficiency of gravitational accretion. Quasars were most common in the early universe, when galaxies had more gas to feed their central black holes, and they are among the most distant objects we can observe, with some quasars visible from when the universe was less than 1 billion years old. The largest known black holes are almost incomprehensibly massive. TON 688, a quasar about 10.4 billion light-years away, contains a black hole with an estimated mass of 66 billion solar masses. Its event horizon is roughly 1300 AU in diameter, that is about 1300 times the distance from the Earth to the Sun, which means the event horizon alone is more than 40 times the size of Neptune's orbit. The black hole at the center of the galaxy Phoenix A has an estimated mass of around 100 billion solar masses, making it one of the most massive black holes ever discovered. These objects are so massive that entire solar systems, with all their planets and moons and asteroid belts, could orbit inside their event horizons without even noticing. Because, for extremely large black holes, the tidal forces at the event horizon are actually quite gentle. You could cross the event horizon of a supermassive black hole and not even realize it, at least not immediately. You would only notice that you could never return. Black holes also warp time in profound ways. According to Einstein's general theory of relativity, the stronger the gravitational field, the slower time passes. Near a black hole, this time dilation effect becomes extreme. If you could hover just outside the event horizon of a black hole and then return to your ship farther away, you would find that while only hours had passed for you, years, decades, or even centuries might have passed in the outside universe, depending on how close you got and how massive the black hole was. This is not science fiction. This is tested, verified physics. GPS satellites in orbit around Earth experience a slightly weaker gravitational field than clocks on the surface, and their clocks tick slightly faster as a result. The GPS system has to correct for this time dilation to maintain accuracy. Near a black hole, the effect is magnified millions of times. And here is one of the most beautiful and haunting thought experiments in all of physics. Imagine you are watching a friend fall into a black hole. From your perspective, far away, you would see them approach the event horizon and appear to slow down. They would seem to move more and more slowly, their image becoming redder and dimmer as the light they emit gets stretched by the extreme gravity. They would appear to freeze at the event horizon, becoming a fading, reddening, ghostly image that never quite disappears, asymptotically approaching the boundary but never seeming to cross it. But from your friend's perspective, nothing unusual happens at the event horizon. They cross it and continue falling inward toward the singularity. The event horizon is not a wall or a barrier, it is just the point of no return, the last place from which light can escape. Once they cross it, they are doomed to fall into the singularity, where the known laws of physics break down and we do not know what happens. This disconnect between what the outside observer sees and what the falling observer experiences is one of the deep mysteries of black hole physics, and it connects to the information paradox, the question of what happens to the information contained in objects that fall into a black hole. Quantum mechanics says information cannot be destroyed, but general relativity says anything that falls into a black hole is lost forever. These two pillars of modern physics contradict each other when it comes to black holes, and resolving this paradox may require a new theory of quantum gravity that unites general relativity and quantum mechanics. It is one of the greatest unsolved problems in physics. Stephen Hawking proposed a possible resolution in the 1970s when he showed theoretically that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit a faint radiation, now called Hawking radiation, which causes them to slowly lose mass and eventually evaporate. For a stellar mass black hole, this evaporation would take an inconceivably long time, about 10 to the power of 67 years, far longer than the current age of the universe. For a supermassive black hole, it would take even longer, 10 to the power of 100 years or more. But in principle, every black hole will eventually evaporate and disappear, leaving behind only a faint bath of radiation. Whether the information that fell into the black hole is somehow encoded in this Hawking radiation, allowing it to be recovered, is still debated. It is called the black hole information paradox, and solving it is considered one of the keys to unlocking the deepest secrets of the universe. Let us now return to our outward journey, because we have been exploring the wonders within our galaxy, and it is time to step outside. It is time to see the Milky Way from the outside, and to understand where it fits in the larger structure of the cosmos. And this is where the scale truly begins to become mind-breaking. Our galaxy, the Milky Way, is not alone. It is part of a collection of galaxies called the Local Group. The Local Group is a gravitationally bound cluster of more than 80 galaxies spanning roughly 10 million light-years. Let me say that again. 10 million light-years. Our galaxy is about 100,000 light-years across, and the group of galaxies we belong to spans 10 million light-years. That is already a factor of 100 larger than our entire galaxy. The Local Group is dominated by two large spiral galaxies, the Milky Way and the Andromeda Galaxy, also known as Messier 31 or M31. Andromeda is the nearest large galaxy to the Milky Way, located about 2.54 million light-years away. That means the light we see from Andromeda today left that galaxy 2.5 million years ago, when our ancestors were still using simple stone tools on the plains of Africa. Andromeda is larger than the Milky Way, with a diameter of about 220,000 light-years, and it contains roughly 1 trillion stars. On a clear dark night, you can actually see the Andromeda Galaxy with your naked eye. It appears as a faint, fuzzy smudge of light in the constellation Andromeda, and it is the most distant object visible to the unaided human eye. When you look at that faint smudge, you are seeing the combined light of 1 trillion suns, from a distance of 2.5 million light-years, and every photon reaching your retina has been travelling through the void of space for 2.5 million years. That is a humbling thought. And here is one of the most dramatic facts about our cosmic future. The Andromeda Galaxy is heading toward the Milky Way at a speed of about 110 kilometers per second. In about 4 to 5 billion years, the two galaxies will collide and merge into a single, larger galaxy, sometimes nicknamed Milkomeda or Milkdromeda. This collision will be a spectacular event by astronomical standards, lasting hundreds of millions of years as the two galaxies dance around each other, their spiral arms distorted by gravitational tidal forces, triggering enormous bursts of new star formation as gas clouds compress and collapse. But here is the counterintuitive and almost unbelievable part. Despite the fact that the Milky Way and Andromeda contain a combined total of roughly 1.5 trillion stars, it is extremely unlikely that any two stars will actually collide during the merger. The distances between stars are so vast compared to the sizes of the stars themselves that the galaxies will pass through each other almost like two ghosts. The stars will be gravitationally shuffled and rearranged, but direct stellar collisions will be vanishingly rare. Eventually, over hundreds of millions of years, the two galaxies will merge into a single large elliptical galaxy, and the night sky, if anyone is still alive on Earth to see it, will look dramatically different, filled with the combined stars of both galaxies in a brilliant, diffuse glow. The third largest member of the local group is the Triangulum Galaxy, or M33, a spiral galaxy located about 3 million light-years from Earth. It is smaller than both the Milky Way and Andromeda, with a diameter of about 60,000 light-years and about 40 billion stars. The rest of the local group consists primarily of dwarf galaxies, small, faint galaxies with anywhere from a few thousand to a few billion stars. The Milky Way has at least 50 known satellite galaxies, small galaxies orbiting within its gravitational influence, including the large and small Magellanic Clouds, which are visible from the southern hemisphere as luminous patches in the sky. The Large Magellanic Cloud is about 160,000 light-years away and has a diameter of about 14,000 light-years. It is the fourth largest galaxy in the local group and was the site of the most recent naked-eye supernova, SN 1987A, which was observed on February 23, 1987. The Milky Way is actively consuming some of its satellite galaxies, a process called galactic cannibalism. The Sagittarius dwarf elliptical galaxy is currently being torn apart and absorbed by the Milky Way's gravity, its stars being stretched into long tidal streams that wrap around our galaxy. This is how galaxies grow over time, by swallowing smaller galaxies. The Milky Way itself was built, in part, from the accumulated remnants of many smaller galaxies consumed over billions of years. Let us now zoom out even further. The local group is not an isolated structure. It is part of a larger collection of galaxy groups and clusters called the Virgo supercluster. The nearest large galaxy cluster to us is the Virgo cluster, located about 54 million light-years from Earth. The Virgo cluster contains about 1,300 to 2,000 galaxies, including several massive elliptical galaxies such as M87, the galaxy whose supermassive black hole was famously imaged by the Event Horizon Telescope in 2019, producing the first ever direct image of a black hole's shadow. M87's central black hole has a mass of about 6.5 billion solar masses. The Virgo cluster is the heart of the Virgo supercluster, and its gravitational influence extends across the entire supercluster. But even the Virgo supercluster is just a small part of a much larger structure. In 2014, a team of astronomers led by R. Brent Tully published a landmark paper defining a new, much larger supercluster of galaxies, the Laniakea supercluster. Laniakea, whose name means immeasurable heaven in Hawaiian, is a vast collection of approximately 100,000 galaxies spanning about 520 million light-years. The Milky Way, the local group, and the Virgo cluster are all part of Laniakea. The supercluster is defined not by a sharp boundary, but by the flow of galaxies. Tully and his colleagues mapped the motions of galaxies in our region of the universe and found that they all flow toward a common gravitational center, an enormous concentration of mass called the Great Attractor. The Great Attractor is located roughly 150 to 250 million light-years from Earth, in the direction of the constellations Centaurus and Hydra. It has been a mystery for decades because it is hidden behind the plane of the Milky Way, which blocks our view with gas and dust. But its gravitational influence is clear. Galaxies in our region of the universe, including the Milky Way, are all moving toward it at several hundred kilometers per second. The Great Attractor appears to be a massive concentration of galaxy clusters, the Norma cluster being one of the most significant, located near the center of this gravitational watershed. But wait, even Laniatea is not the biggest structure out there. Not by a long shot. As we zoom out to the largest scales, the universe reveals a structure that is both beautiful and almost beyond comprehension: the cosmic web. The cosmic web is the large-scale structure of the universe, a vast, three-dimensional network of filaments, walls, nodes, and voids that spans the entire observable universe. Imagine a three-dimensional spiderweb stretching in all directions, with thick threads connecting massive junctions and enormous empty bubbles in between. The filaments are long, thin threads of galaxies and dark matter, stretching tens to hundreds of millions of light-years, connecting galaxy clusters to each other. The nodes where filaments intersect are the locations of the most massive galaxy clusters, containing thousands of galaxies. The walls are flat, sheet-like arrangements of galaxies connecting filaments. And the voids are enormous, roughly spherical regions of space that are almost completely empty, vast bubbles of nothingness, hundreds of millions of light-years across, with very few galaxies inside them. The cosmic web is the largest pattern in the universe. Some of the largest known structures include the Hercules Corona Borealis Great Wall, a vast wall of galaxy clusters that is about 10 billion light-years across, making it the largest known structure in the observable universe. The Sloan Great Wall, discovered in 2003, is about 1.4 billion light-years long, and the largest known void, the KBC void, may extend up to 2 billion light-years in diameter, an almost inconceivably vast region of space, with significantly fewer galaxies than average. These structures exist on scales so large that they challenge our understanding of how the universe evolved, because the standard model of cosmology sets limits on how large structures can be, based on the age of the universe and the speed at which gravitational collapse can operate. The existence of structures approaching or exceeding 10 billion light-years raises questions that are still being debated. And here is what makes the cosmic web truly remarkable. Its structure was seeded in the very first moments of the universe's existence. During the Big Bang, or more precisely, during the period of cosmic inflation that is thought to have occurred a tiny fraction of a second after the Big Bang, quantum fluctuations, random variations in the density of energy at the subatomic scale, were stretched to cosmic proportions. These tiny variations became the seeds of all structure in the universe. Slightly denser regions had slightly more gravity, which attracted more matter, which increased their density further, attracting even more matter, in a process of gravitational amplification that played out over billions of years. The filaments of the cosmic web trace these primordial density fluctuations, stretched and amplified across 13.8 billion years of cosmic evolution. The largest structures in the universe are, in a very real sense, quantum fluctuations writ large. The patterns you see in the cosmic web are echoes of the subatomic world, magnified to scales spanning billions of light-years. That connection between the inconceivably small and the inconceivably large is one of the most profound insights in all of science. Computer simulations of cosmic structure formation, such as the Millennium Simulation, the Illustris project, and its successor Illustris TNG, have been able to reproduce the cosmic web with remarkable fidelity. These simulations start with the initial conditions inferred from observations of the cosmic microwave background, the afterglow of the Big Bang, and then use the laws of physics to evolve the universe forward in time, tracking the formation of dark matter halos, galaxies, stars, and the large-scale structure. The results match observations beautifully, giving us confidence that our understanding of the basic physics governing the universe is correct, at least on large scales. Now let us tackle one of the most mind-bending concepts in all of cosmology, the observable universe. The observable universe is the region of the universe from which light has had time to reach us since the Big Bang, 13.8 billion years ago. You might think that this means the observable universe has a radius of 13.8 billion light years after all. If the universe is 13.8 billion years old, then the farthest light can have travelled is 13.8 billion light years, right? Wrong. And understanding why is one of the most important and most commonly misunderstood aspects of modern cosmology. The key is the expansion of the universe. The universe is not static. Space itself is expanding. This expansion was discovered by Edwin Hubble in 1929, when he observed that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This is not because the galaxies are moving through space like rockets. It is because the space between galaxies is stretching, carrying the galaxies along with it, like dots drawn on a balloon that is being inflated. This expansion is happening everywhere in the universe, between every pair of distant galaxy clusters. The expansion does not happen within galaxies or within gravitationally bound structures like the local group. Gravity overcomes the expansion on those scales. But on the largest scales, between galaxy clusters and superclusters, space is stretching, and the farther apart two objects are, the faster the space between them is expanding. This means that the light from the most distant objects we can see has been travelling through expanding space for 13.8 billion years. During that time, the space through which the light was travelling has been stretching, so the objects that emitted that light are now much farther away than 13.8 billion light years. The current best estimate for the radius of the observable universe is about 46.5 billion light years. That means the observable universe has a diameter of about 93 billion light years. The most distant objects we can see are now about 46.5 billion light years away, even though the light from them has only been travelling for about 13.8 billion years. The extra distance is due to the expansion of space during the time the light was in transit. This is not a violation of the speed of light. The speed of light is a local speed limit. Nothing can move through space faster than light. But space itself can expand at any rate, and the cumulative expansion of all the space between us and a distant object can cause that object to recede from us faster than the speed of light. In fact, objects beyond a certain distance, called the Hubble radius, are currently receding from us faster than light. We can still see them because their light was emitted when they were closer and the expansion was slower, so the light managed to reach us even though the source has since been carried beyond our reach by the expansion of space. The rate at which the universe is expanding is described by the Hubble constant, currently measured at about 67 to 73 kilometers per second per megaparsec, depending on the method of measurement. A megaparsec is about 3.26 million light years. This means that for every 3.26 million light years of distance between two objects, the space between them is expanding at about 67 to 73 kilometers per second. For nearby objects, this expansion is negligible, but for objects billions of light years away, the cumulative expansion adds up to enormous recession velocities, and this creates a profound consequence for the future of the universe. Objects that are currently visible to us, objects whose light has reached us, will eventually be carried so far away by the expansion of space that their light will no longer be able to reach us. The observable universe will shrink over time. In the very far future, trillions of years from now, if the expansion continues to accelerate as it is currently doing, other galaxies will have receded so far that their light will be redshifted into oblivion, becoming undetectable. A civilization arising in the far future in our galaxy would look out at the sky and see nothing but their own galaxy, surrounded by perfect darkness. They would have no way of knowing that the universe once contained hundreds of billions of other galaxies. The evidence would simply be gone, erased by the expansion of space. We live in a special time, a brief window in cosmic history, when the universe is young enough and the expansion slow enough that we can still see the vast cosmic tapestry. In the future, that tapestry will be invisible. Let me give you a sense of how many galaxies are out there. Within the observable universe, current estimates suggest there are approximately 200 billion to 2 trillion galaxies. Let me let that number sink in. 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. The total number of stars in the observable universe is estimated to be around 200 billion trillion, that is 2 times 10 to the power of 23, or 200 sextillion. That is more stars than there are grains of sand on all the beaches and deserts of Earth. And each of those stars may have planets. The total number of planets in the observable universe could be on the order of 10 to the power of 24, or 1 septillion. 1 septillion planets. And the observable universe is just the part of the universe we can see. The actual universe, the totality of everything that exists, may be vastly larger than the observable universe, perhaps infinitely larger. We do not know. We cannot know, because the light from those regions has not had time to reach us, and, if the expansion of the universe continues to accelerate, it never will. And here is where things get really strange. The expansion of the universe is not just continuing, it is accelerating. In 1998, 2 independent teams of astronomers studying distant Type I supernovae, standard candle explosions whose brightness can be used to measure cosmic distances, made a shocking discovery. The expansion of the universe is not slowing down, as everyone expected. It is speeding up. The most distant supernovae were dimmer than expected, meaning they were farther away than predicted by a universe expanding at a decelerating rate. Something was pushing the expansion to go faster and faster. This mysterious force was dubbed dark energy, and its discovery earned Saul Perlmutter, Brian Schmidt, and Adam Ries the Nobel Prize in Physics in 2011. Dark energy is one of the greatest mysteries in all of science. It makes up about 68% of the total energy content of the universe, yet we have essentially no idea what it is. It behaves like a property of space itself, a kind of anti-gravity that becomes stronger as the universe expands and space becomes more plentiful. The simplest model for dark energy is the cosmological constant, originally proposed by Einstein and then abandoned, which represents a constant energy density of empty space, the energy of the vacuum. But whether dark energy is truly constant or whether it changes over time is one of the major open questions in cosmology. And the implications are profound. If dark energy continues to accelerate the expansion of the universe, then the ultimate fate of the cosmos is a cold, dark, lonely end. Galaxies will recede from each other, stars will burn out, and the universe will slowly fade into a state of maximum entropy, sometimes called the heat death of the universe. And dark energy is not the only mysterious component of the universe. There is also dark matter. Dark matter is a form of matter that does not interact with light or any form of electromagnetic radiation, making it invisible. We cannot see it, we cannot detect it directly, but we know it exists because of its gravitational effects. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. Galaxies rotate too fast. The stars in the outer regions of galaxies orbit at speeds that should fling them out into space if the only gravity holding them in were from the visible matter. But they don't fly apart, which means there must be additional invisible mass, providing extra gravity. Galaxy clusters contain far more mass than can be accounted for by the visible galaxies and hot gas within them, as determined by gravitational lensing, the bending of light from background objects by the cluster's gravity. And the pattern of fluctuations in the cosmic microwave background can only be explained if the universe contains about 5 times more dark matter than ordinary matter. Current estimates suggest that ordinary matter, the atoms that make up stars, planets, and people, constitutes only about 5% of the total energy content of the universe. Dark matter makes up about 27%, and dark energy makes up the remaining 68%. This means that everything we can see, everything we have ever observed with our telescopes, every star. Every galaxy, every planet, every nebula, every human being, all of it makes up less than 5% of what the universe actually contains. 95% of the universe is made of stuff we cannot see and do not understand. That is a profoundly humbling realization. Let us now turn to the most ancient light in the universe, the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, radiation that was emitted about 380,000 years after the beginning of the universe, when the cosmos had cooled enough for the first atoms to form and for light to travel freely through space for the first time. Before this epoch, called the era of recombination, the universe was a hot, dense, opaque plasma of protons, electrons, and photons, all tightly coupled together. Photons could not travel far before being scattered by free electrons. But when the temperature dropped below about 3000 Kelvin, electrons combined with protons to form neutral hydrogen atoms, and suddenly the universe became transparent. The photons that were released at that moment have been traveling through space ever since, cooling as the universe expanded, and they now form a nearly uniform glow of microwave radiation that fills the entire universe in every direction, with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. This radiation was predicted theoretically in the 1940s and accidentally discovered by Arno Penzias and Robert Wilson in 1965, earning them the Nobel Prize. The CMB is the oldest light in the universe. When we observe it, we are looking back to a time just 380,000 years after the Big Bang, seeing the universe as it was 13.4 billion years ago. And the CMB is not perfectly uniform. It has tiny fluctuations in temperature, on the order of 1 part in 100,000, which correspond to slight variations in the density of matter in the early universe. These fluctuations are the seeds from which all cosmic structure grew, the galaxies, galaxy clusters, filaments and voids that we see today. Maps of the CMB, produced by missions such as COBE, MAP and Planck, are essentially baby pictures of the universe, showing the initial conditions from which everything we see around us evolved. The information encoded in the CMB has allowed cosmologists to measure the age of the universe, the rate of expansion, the total amount of matter and energy, the curvature of space, and many other fundamental properties with remarkable precision. It is, without exaggeration, the single most important observation in the history of cosmology. The Big Bang itself is the starting point of our understanding of the universe, and it is one of the most misunderstood concepts in all of science. The Big Bang was not an explosion in space like a bomb going off in an empty room. It was an expansion of space itself. At the very beginning, roughly 13.8 billion years ago, the observable universe was compressed into an unimaginably small, hot, dense state, and then it began to expand. There was no center of the explosion, because the expansion happened everywhere simultaneously. Every point in the universe was the center of the expansion, and there was no empty space outside the universe into which the expansion occurred. Because the universe is all of space, it does not expand into anything. Space itself is what is expanding. In the first fraction of a second, the universe went through a period of incredibly rapid expansion called cosmic inflation, during which it expanded by a factor of at least 10 to the power of 26 in a tiny fraction of a second. This inflation smoothed out any large-scale irregularities and set the stage for the universe we see today. After inflation ended, the universe continued to expand and cool. Within the first few minutes, a process called Big Bang nucleosynthesis produced the lightest elements, hydrogen, helium, and tiny amounts of lithium and beryllium. For the next few 100,000 years, the universe was a hot, glowing plasma until it cooled enough for atoms to form and the CMB was released. Then, over hundreds of millions of years, gravity slowly pulled matter together, forming the first stars, the first galaxies, and eventually the vast cosmic web we observe today. The first stars, sometimes called population the 3 stars, are thought to have formed about 100 to 200 million years after the Big Bang. These stars were unlike any stars we see today. They formed from the pristine gas of the early universe, which contained only hydrogen, helium, and trace amounts of lithium, no heavier elements at all, because heavier elements are only produced inside stars and in stellar explosions. Without heavier elements to help cool the gas and fragment it into smaller clumps, the first stars are thought to have been extremely massive, perhaps hundreds or even 1,000 times the mass of our Sun. These stellar giants burn through their nuclear fuel quickly, in just a few million years, and then exploded as supernovae, scattering the first heavier elements into the surrounding gas. Some may have been so massive that they collapsed directly into black holes, which could have been the seeds of the supermassive black holes we see at the centers of galaxies today. We have not yet directly observed any population of 3 stars. They burned out and died long ago, and even with our most powerful telescopes, we can only barely see the era when the first galaxies were forming. The James Webb Space Telescope, launched in December 2021, has been peering deeper into the early universe than any telescope before, discovering galaxies that existed just a few 100 million years after the Big Bang, much earlier than many models predicted. These early galaxies are surprisingly bright and massive, challenging our understanding of how quickly galaxies can form and grow, and they may contain clues about the first generation of stars. Let us now step back and appreciate the full scale of what we have traversed. We started on the surface of the Earth, a thin crust of rock on a small planet in the inner solar system. We traveled to the Moon, 384,000 kilometers away. We visited the planets from Mercury to Neptune, spanning a distance of about 4.5 billion kilometers. We passed through the Kuiper Belt and into the theoretical Oort cloud, which may extend 100,000 AU, or about 1.5 light-years, from the Sun. We crossed the interstellar void to the nearest star, 4.25 light-years away. We zoomed out to see our local stellar neighborhood, then the largest structure of the Milky Way, 100,000 light-years across. We saw our galaxy as part of the local group, 10 million light-years across. We saw the local group as part of the Virgo supercluster, and the Virgo supercluster as part of the Laniakea supercluster, 520 million light-years across. We saw Laniakea as just one cell in the vast cosmic web. And finally, we confronted the observable universe itself, 93 billion light-years in diameter, containing 2 trillion galaxies and 200 sextillion stars. Each step was a leap by factors of thousands or millions. Each step made the previous one seem infinitesimally small. And here is the thing that should really get you. The observable universe may be just a tiny fraction of the actual universe. Current observations suggest that the universe is either flat or very close to flat, which means it may be infinite in extent. If the universe is truly infinite, then there are infinite galaxies, infinite stars, infinite planets, stretching out forever in all directions. The observable universe, vast as it is, would be just an infinitesimal patch of an infinite cosmos. And even if the universe is not infinite, but merely much larger than the observable portion, the actual universe could be so large that the observable universe is to the actual universe as a proton is to the entire observable universe. We simply do not know. Let me now take you on a more contemplative journey through some of the most profound implications of cosmic scale, because the numbers and distances we have discussed are just the beginning. The real depth lies in what these numbers mean for our understanding of existence, of time, of life, and of our place in the cosmos. Consider the speed of light, the cosmic speed limit. Light travels at about 300,000 kilometers per second. At that speed, a beam of light could circle the Earth 7.5 times in a single second. It is the fastest speed at which information, energy, or matter can travel. And yet, at this ultimate speed, it takes light 4.25 years to reach the nearest star. It takes light about 26,000 years to reach the center of our galaxy. It takes light about 2.5 million years to reach the Andromeda galaxy. It takes light about 13.4 billion years to reach us from the most distant objects we can observe. The light from those objects was emitted when the universe was only a few 100 million years old, when the first stars and galaxies were just beginning to form. When we look at distant objects, we are looking back in time. A telescope is a time machine. Every photon that reaches our eyes or our instruments carries information from the past, from the moment it was emitted. When you look at the sun, you see it as it was 8 minutes and 20 seconds ago. When you look at Sirius, you see it as it was 8.6 years ago. When you look at the Andromeda galaxy, you see it as it was 2.5 million years ago. When we observe the cosmic microwave background, we see the universe as it was 13.4 billion years ago. And we can never see the universe as it is right now, because light takes time to travel, and the universe is so vast that right now is a concept that barely has meaning on cosmic scales. By the time we see a distant galaxy, hundreds of millions of years may have passed for that galaxy. Its stars may have changed, its black holes may have grown, civilizations may have risen and fallen, and we would have no way of knowing, because the light carrying that information is still on its way. This leads to one of the most haunting realizations about the universe. There is a region of the universe beyond the cosmic event horizon, the boundary beyond which the expansion of space carries objects away from us faster than light can ever bridge the gap. Light from objects beyond the cosmic event horizon will never reach us, no matter how long we wait. Those regions of the universe are lost to us forever. And as the expansion of the universe accelerates, the cosmic event horizon is getting closer. More and more of the universe is being pushed beyond our reach with every passing moment. The observable universe is shrinking, in the sense that fewer and fewer distant objects will be visible to us in the future. In the far future, the only galaxy visible from the Milky Way will be the product of the Milky Way-Andromeda merger, because every other galaxy will have been carried beyond the cosmic event horizon by the accelerating expansion of space. Future astronomers, if any exist, will look out at the sky and see a single galaxy floating in a vast, empty, dark void. They will have no evidence that the universe was ever any different. The cosmic story, the evidence of the Big Bang, the CMB, the large-scale structure, all of it will be invisible, erased by the expansion of space. We live in a privileged era, a brief window of cosmic time when the clues to the universe's origin and evolution are visible. This is not a coincidence, it is a selection effect, since intelligent life requires complex chemistry that takes billions of years to develop, and so we necessarily exist in an era when the universe is old enough for us, but young enough for the evidence to still be visible. But the window will not remain open forever. Let us talk about the far future of the universe, because the scale of the universe is not just about space, it is also about time. The universe is 13.8 billion years old. That is a long time by any human standard. But in terms of the universe's total lifespan, assuming the current models are correct, we are living in the extreme infancy of cosmic history. The stelliferous era, the age of stars, began a few 100 million years after the Big Bang, and will last for roughly 100 trillion years, about 10,000 times longer than the current age of the universe. During this era, stars will continue to form, burn and die. But the rate of star formation is already declining. The peak of star formation in the universe occurred about 10 billion years ago, and it has been declining ever since. We are already past the cosmic noon of star creation. In the far future, hundreds of billions of years from now, the galaxies will have exhausted their reserves of star-forming gas. The last stars to form will be small, dim red dwarfs, which burn their fuel so slowly that they can shine for trillions of years. Long after the sun has died and the solar system has gone dark, these tiny red dwarfs will still be glowing faintly, the last embers of the stelliferous era. But eventually, even the red dwarfs will exhaust their fuel and fade out. The last star in the universe is expected to die about 100 trillion years from now. After that, the universe will enter the degenerate era, an age of darkness populated only by the cold remnants of dead stars, white dwarfs, neutron stars and black holes, along with planets, asteroids and other debris, all slowly cooling and drifting through an ever-expanding, ever-darkening cosmos. In the degenerate era, which will last an almost inconceivable length of time, the universe will slowly decay. White dwarfs will cool into black dwarfs, objects so cold that they no longer emit any detectable radiation. Neutron stars will cool as well. Protons, the fundamental building blocks of ordinary matter, may themselves decay. If proton decay occurs, as some grand unified theories predict, with a half-life of perhaps 10 to the power of 36 to 10 to the power of 41 years, then, over immense timescales, all ordinary matter will eventually disintegrate into leptons and photons. Planets, asteroids, white dwarfs, neutron stars, everything made of ordinary matter will eventually dissolve. The universe will consist only of black holes, a thin bath of particles and radiation, and endless expanding empty space. In the black hole era, from about 10 to the power of 40 to 10 to the power of 100 years from now, the only remaining objects of significance will be black holes. They will slowly evaporate through Hawking radiation, their lifetimes dependent on their mass. A stellar mass black hole will evaporate in about 10 to the power of 67 years. A supermassive black hole of 1 billion solar masses will take about 10 to the power of 98 years. The most massive black holes will be the last macroscopic objects in the universe, slowly shrinking, slowly radiating, their event horizons glowing with an impossibly faint warmth. And then, in the final moments of each black hole's life, as it shrinks to the smallest size, it will emit a burst of radiation and then vanish entirely, leaving behind nothing but photons and particles. After the last black hole evaporates, the universe enters the dark era, an epoch of almost absolute nothingness. The universe will consist of a thin, ever-cooling, ever-diluting bath of photons, neutrinos, and perhaps some exotic particles like positronium atoms, weights of an electron and a positron that will eventually decay. The temperature of the universe will asymptotically approach absolute zero, but never quite reach it. Space will continue to expand, the distances between particles will continue to grow, and the universe will become an increasingly cold, empty, dark and silent place, stretching out for timescales so long that even scientific notation struggles to convey them. 10 to the power of 100 years, 10 to the power of 1,000 years, 10 to the power of 10 to the power of 100 years. The numbers become meaningless, but the universe will still exist, a vast, dark, cold expanse, expanding forever, with nothing happening, no structures, no complexity, no life, no light. Just the slow, inexorable approach toward maximum entropy, the heat death of the universe. That is the ultimate fate of the cosmos, according to our current best understanding. It is a bleak picture, and it can feel overwhelming. But let me offer a different perspective. We exist now, in this tiny, extraordinary window of cosmic time, when the universe is filled with light and structure and complexity and life. We are made of atoms forged in stars, organized by billions of years of evolution into beings that can contemplate the very universe that created them. We can look up at the night sky and see the light of galaxies billions of light years away. We can build telescopes that peer back to the dawn of time. We can write equations that describe the behavior of the cosmos from the first fraction of a second to the far future. We are the universe becoming aware of itself. And that is not a small thing. That may in fact be the most extraordinary thing that has ever happened in the history of the cosmos. In a universe that is overwhelmingly vast, overwhelmingly old, overwhelmingly empty, and overwhelmingly dead. Here we are, alive, curious, aware. The universe has produced at least one place, and possibly many more, where matter has organized itself into something that can ask why. That is a miracle, not in the supernatural sense, but in the deepest, most honest sense of the word. Something so improbable, so extraordinary, so beautiful, that it takes your breath away.